Welcome to your PN39 notes. This is part A of a two-part series of a series on vectors. This is associated with 6.1 in your textbook. And at the very top, it kind of talks a little bit about what we're doing here. It says we're working with a lot of quantities in mathematics, or we have worked with them. We've worked with height, area, volume, temperature, time, all those kind of good things. However, there are some measurements that require a size and a which is we'll call a magnitude, and a direction, such as force, velocity, or acceleration. These values get represented as vectors and are particularly useful in physics and other sciences, and I will put a plug in for engineering for sure, and also calculus. We will learn some of the basics about vectors to have you get ready to apply these skills elsewhere. So if you haven't taken a physics course yet, this will prepare you for that. If you have taken a physics course, what's really nice about that this is that it will reinforce some of those skills that you have seen in those courses. Now a vector is represented in component form. It looks just like that right here. And it's a directed line segment or a ray. You're very familiar with rays from geometry, and it goes in this case from point 0, 0 to the point AB. So let's just say AB is right here, and we're going to create a vector of that length, and notice that the direction is that going up to the right. So not only does a vector have a magnitude, which we'll right now call, we really don't want to necessarily say length, but we typically say size, because that length size is actually representing force, velocity, acceleration. So if students start thinking of it in terms of length, it kind of gets them into trouble. But anyway, so this here, if you look at this, if I create a right triangle by bringing this this line down, or from the point, and look at the horizontal movement, that is our A movement, or A length, and this is our B, or vertical movement, to get to that point AB. So that movement, that horizontal movement and vertical movement, is vector AB in component form. So down here, it's going to say sketch the vector in standard position from the origin. And I do want to say that when you hear standard position, that means that we're starting at 0, 0. So we're starting at 0, 0. We have a horizontal movement of -5. We have an upward vertical, 1, 2, 3, 4, 5, vertical movement of 5. So we're going to end up with a point right up here. And now remember, this is not, right here, this is not a point per se, this is a vector. So we are going to sketch that vector in standard form starting at 0, 0. So it starts at 0, 0, and it will go all the way to -2, 5. And the vector is, and you know what, I'm going to color code it. The vector is this, a ray, in the direction up to the left. And right now we're just going to say up to the left, but eventually we're going to be giving bearings and or directional angles, and we'll be talking about that actually in part B, kind of like a spoiler there for a bit. Example number 2. It says sketch the vector RS if point R, which is 5, 3, and S point is 2, -1. Rename this vector into this notation. That's component notation. And then who, and it's actually saying what or who is the initial point and who is the terminal point of this R and S. And I just want to say this is what lets you know who's the initial and who is the terminal. The initial is R because that's the beginning, where we're starting, and S is the terminal because that's where we're ending. What direction does that arrow go? Well, you know what? My advice is always is to sketch it really quick. So I have 1, 2, 3, 4, 5, 1, 2, 3. There is my R point. My terminal point, which is S, is at 2, -1. And this vector, because it starts, and I'm going to change colors here, because it starts at R and ends at S, notice that we have a downward to the left. Our direction is a downward to the left direction. Ooh. Have to push a little harder there. Okay, so that's the answer to that last question. But we still need to do this right here, which is rename the vector into that component notation. And so now when it's in standard form, it's really easy to see. I mean, that's pretty straightforward to do. But when it's not in standard form, what you really want to do is you need to look at, and I think, again, I'm going to switch colors here really quick. so you can see what I'm doing. I'm going to create a right triangle with this vector. And if you look at it, we're starting again right here at this point. We're going to be going, and again, this is going to be your horizontal movement, this is your vertical movement of your vector. And so I can see that I am going, let's see, I have 5, 1, 2, 3. We're going back 3 on the x-axis, or the horizontal axis, and we're going down, how many there? 4 on the vertical axis. So what you can think about is we've got this movement. There's your vertical movement, which is -4. And remember, your vertical goes along as the second spot, and your horizontal movement is -3. But you do need to get this component form, you need to make sure you know what your initial spot is, which is R, and where your ending point or your terminal point is, which in this case is S. So that's how you're going to rename the vector if it is not in standard form, is create that right triangle with that vector. Now there is another trick, and I'm going to show that here in example number 3. It says if you have point P, which is 4, -3, and notice that's the initial point, and I know that because I'm looking at that right there. So I'm going to remind myself that that's the initial point. And it's represented by the vector, so this is the vector right there. Oops. And I want to find Q, and the Q is the terminal point. So we could graph that initial point and then do the movement to -4 on that to find where you end up. And so you can definitely graph this, and just like we did example number 2, but kind of working backwards. Or you can think about this logically and say, hey, you know what? I have an initial point. I know that if I add my vector to it, my movement, oh, I keep doing that, my vector to it, I'm going to end up with my terminal point. So my initial point here is 4, -3. Oops, it's a point, not a vector, plus the vector movement of 2, -4 will get you to your terminal point. And if you add those together, literally adding them together, you'll end up with 6, -7. And if you were to graph it, it would instill that exact thing. So this is kind of right here. Let me highlight this so you can see it a little bit better. This right here is a really nice thing to have. Because if you think about it again, if you start at an initial point, you add your movement, your vector, almost thinking like in terms of slope, if you will, to get to that terminal point, you can then find your terminal point very algebraically. And we could have done that up here in example number 2, but the difference is you would have put in values for the initial point and the terminal point and done your algebra to find the vector, and you would have gotten -3, -4 as well. So whether you want to use graphing or algebra does not matter, just as long as you can get to that right answer. Okay, so now down here it says we mentioned that vectors have magnitude and direction. Refer to example 2 from above. What do you think it means to find the magnitude of RS? So the magnitude of RS. How can we find that value? So I'm just going to come back up to here, example number 2. We know that the horizontal and vertical movement was -3, -4. We know that. But the actual magnitude, the magnitude, as I've kind of already alluded, is, ooh, that's horrible. Let's try a different color. Is this length, or actually, remember I said I probably shouldn't use the word length, size, this size. And if you look at that, that will be the magnitude, and what you do is you have a right triangle, and of course if we have two sides of a right triangle, we just use Pythagorean theorem to find the magnitude or the size. So let me go back to a reasonable color here and remind you, and again I'm just going to remind you that RS, the vector RS from example number 2 is the component -3, -4. Now it wasn't initially drawn in standard form, so I am going to actually draw it in standard form. It's really a good idea to do that. 1, 2, 3, 1, 2, 3, 4, so you can kind of really see what you're doing. And -3, 4. All of a sudden I was looking at, oh, I missed my sign, didn't I? Ooh, I was looking at example number 2. Sorry, you guys. So it's -3, -4. Let me erase that point right there. That's not where we're going. We are going to go -3, 1, 2, 3, 4 down here. Let's see, that looks a lot better. Okay, and again, I'm going to change colors just so you can see my vector nice and clear. Now again, I want the magnitude. So the magnitude again is that orange length right there. So I'm going to create a right triangle, always to the x-axis, always connecting to the x-axis. We know that this here is -3 this way, -4 this way. So if we use Pythagorean theorem, oops, plus -4 quantity squared will give me my magnitude. Now this is where I'm going to introduce a notation. We represent magnitude by the absolute value symbol with the vector inside of it. So when you see this notation right here, please know that that means magnitude. And I'll put that right here. I'm going to run out of space here. Actually, I'm going to do right down here. Magnitude. Okay, so that is the magnitude notation. And so when we calculate that out, so if you take and use the Pythagorean theorem to find it, you'll realize really quickly that your magnitude, or the length of that, or the size of that orange vector, is going to be 5. Oops, let me switch it over. Which is the magnitude of RS. Okay, so that's a biggie right there. By the way, if you didn't want to graph it, now I'm kind of a grapher. If you didn't want to graph it, and if you had the two endpoints, the initial point and the terminal point, you could use the distance formula. I mean, and I'm going to write it right here. So the distance formula, which is just based off of the Pythagorean theorem anyway, is x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. That's a minus right there. So the distance formula also works. It's just Pythagorean theorem is way, way, way faster, and it's much more consistent as we move forward. Okay, so at the bottom, example number 4. Well, actually, if you flip it over here, example number 4. It says find the magnitude of vector -3, -7. So this right here, this example 4, this is on you. So you're doing this following what we did in example number 3 and right below that. So do graph it, do use Pythagorean theorem, leave it in exact form. So I want to see a graph and I want to see your magnitude with the proper notation. So you're going to be showing me that in class. So make sure you graph it, graph the vector, and then find the magnitude of this vector. And since there's no name, I'm just going to use V for the vector. Right here it says find the magnitude of PQ. If P is this point and Q is this point, this is where you could use the distance formula if you want, or you can find the component vector of this point, or this vector. So I'm just letting you know you can definitely find this first, which is what we did in example number 2. And once you do that, then you can graph it and then find the magnitude. So you do want to first find the component. Once you have the component of PQ, so this is the PQ vector component, and then from there find the magnitude of PQ. And again, you can do this, keep it in exact notation, so there's going to be a square root, but make sure to simplify that. Okay, so those two you're going to be showing me in class next time we meet. Down here where it says combining vectors together, this is pretty straightforward from at least what we were just doing, where when you have, and we use this all the time with vectors, when you have multiple forces working with and against each other, that means that your forces will need to be combined. And so what's great about this is, let's say, for instance, you are taking a boat across the river at this speed and direction, and then you have this river that has a kind of a current that's doing this to you, or is going down this direction, so that your boat actually is not just going across like the red one, it's actually being affected by the current, and you end up on with this type of speed and direction. And we'll talk a lot about that in the next section, but I just want to let you know these are combining vectors. It's very, very powerful and very, very useful. It seems very easy initially, but I just want to let you know that this is not somewhere where you really need to understand what you're doing. It's important. It's all important, of course, but okay, so it says find the resultant vector. So when you're combining vectors, we call it a resultant vector, u plus v, where u is -1, 3, and v is 4, 7. Sketch a picture. So what I'm going to do is I'm going to first, by the way, this kind of important, it says make sure your vectors always connect head to tail. Remember, direction matters. So typically we wouldn't have to graph each one of these, but let's do it just to kind of see what's happening here. And again, I'm going to switch colors just so you can kind of see. And it asks you to draw a picture. So let's draw the vector 0, or excuse me, the u vector first. So I have a -1 movement, 1, 2, 3 movement. So here is my u vector. And now I want to add the vector force v to this u vector. And I'm actually even going to put u here so that you see it. And then I'm going to switch colors here for the v vector. The v vector is going to be in green. Actually, watch this. It may get fancy. I can't remember what color I did. There we go. So the v vector, you're doing 4, 7. You're going 4, 7 off of this u vector. So you're going to go 1, 2, 3, 4. So notice I'm coming off of this head and counting over 4 and then up 7. And this is going to be really like awkward because it's like 1, 2, 3, 4, 5, 6, 7. So it's going to be way up here. This is not the best picture. But notice that this vector, the green vector, is coming off of the head of the u vector. And the new resultant vector will be my favorite color, which is red, right here. So what we are trying to do is find this resultant vector. So to make a long story short, all you do is to find the sum, and don't blink because you're going to miss it, is you're literally going to add the two vectors together. Oops, let me do that. Or at least add the two components together. Now you do need to be in component form to do this. So a lot of people try to skip away from getting it into component form, but you need it in component form in order to do this process. So we end up with a vector of 3, 10. And if you look at this red vector, look at 1, 2, 3 over 10 up will give you that red resultant vector, which is awesome. So this right here is the answer. Okay? Okay, so let me just show you a couple. It says use the same vectors u and v from above and find each. Well, you know, if you want to find the scalar of 2u, you take 2 times the vector u, and the vector u in component form is -1, 3. You need to be in component form, and multiply it through. So you just have -2, 3. And I do want to point out down here, notice that if this is the u vector, and if you multiply it by a scalar of 2, you're not changing the direction, you're just doubling the size of it, which means if it were a velocity, you'd be doubling the velocity. You can do this one right here, so you're multiplying through the v vector by -5. And then this one right here, well, take care of this right here, multiply the u vector by 3 and the v vector by 2 and add them, and you are done. So those starred ones along with the top two I will be checking in class. In addition, you're going to be going to section 6.1 in the book and doing numbers 5 through 19 odds to demonstrate that you are understanding this material. Thank you for tuning in, and we'll talk in class with any questions you might have. Take care.